Hello, everybody. Today, we're going to talk about how we're leveraging the new Snowflake ML capabilities for our feature engineering practice. I'm Linda Devenny. I'm a data architect with the Enterprise Data Architecture COE in Fidelity Investments. I, along with my colleague Ray Zhang, who's a chapter area leader in feature engineering, will walk you through some of our techniques that we have developed within Snowpark ML. So we're going to have kind of 4 sections in our presentation today. I'm going to kind of give a brief overview of our data science platform journey, and then talk about some of the core guiding data architecture principles for this platform. The next section, we will have a look at feature engineering within the model development phase of the AI ML lifecycle, including what Snowpark ML is. I'm going to walk through some of the data processing design patterns, and then finally Ray will walk through some of these techniques implemented within some of the data processing patterns. So about 8 years ago, all our data science work was typically done on local physical servers. Then with the advent of Hadoop, we established an enterprise Hadoop cluster on-premise, where the data scientists leveraged a lot of kind of Spark clusters and some of the more unstructured data. Then, back in 2020, we took an enterprise decision of moving to the cloud, where we established an enterprise data lake, along with the concept of data science data labs. And this is very important for our data scientists because unlike traditional SDLC lifecycle, data scientists require access to production data. Now that we're ingesting a large volume of data, our focus at the moment is looking at distributed processing across this platform. So we have the data science platform in place. Now, I, as a data architect, have to look at establishing some key guiding principles for our data scientists and our data engineers alike. Here's 2 of our core principles, one for storage and one for compute. So our enterprise direction is for all structured and semi-structured analytical data, that has to be stored in Snowflake. So we leverage our data security framework, our data governance, and also it provides a holistic approach to metadata management. From a compute perspective, we really want to try and minimize the transfer of data across network and avoid duplication of data where possible. So one of our key strategic decisions is to process the data in place, in database processing. So we're bringing the compute to the data, not the other way around. So I'm going to talk today about feature engineering within model development. I'm not talking about feature store platform integration into model operationalization, just more the kind of key feature engineering subtask within model development. So here, it's not an exhaustive list, but here are some of the common feature engineering techniques our data scientists do within this phase. And we're going to focus on the 3 bottom techniques. These are the most common techniques in use. Encoding, scaling, and also correlation analysis. So from a compute perspective, we've got a few pain points. So data scientists typically use the Pandas data frame object to do a lot of their feature engineering. This is a very flexible data structure, but we're restricted by memory of our notebook environment, along with single node processing, so we can't distribute our processing. There are data scientists who use Spark ML purely for the flexibility of distributed processing. And what we want is we want to look and have the best of both worlds from these 2 approaches. At the moment, we don't have that. There is a large overhead in maintaining our Spark clusters. So I'm going to talk now about Snowpark ML. So last year we evaluated the Snowpark for Python API. And we were very excited with the Snowpark data frame concept that allowed us to create and establish a session with our Snowflake data and also do some of the common analytical functions in database processing, pushed down to the database. While Snowpark data frames are flexible, we soon realized that to leverage some of the, say, common feature engineering techniques available in scikit-learn, for example, we had to convert our Snowpark data frame to pandas. So the minute we did that, we're moving data out of Snowflake and into our notebook environment memory. So it's a kind of a, it's still moving, transferring the data out. So early this year, we worked closely with the Snowflake ML engineering team, and some of the people are here in the room. Garrett Frere, Sandeep, Pradeep Duraj, and Ed Crean. This is the Snowpark ML engineering squad. And we talked about really trying to use the flexibility of Pandas data frames, but with distributed data operations. So we worked with Snowpark ML in private preview. And as you might have heard yesterday in the keynote, this has now become public preview and is available from PyPI as of now. It's an additional library to Snowpark, and you can just do a pip install and you will get some of the ML functionality within this API. All the computation is done in database, and it can deal with large volumes of data. It will scale both vertically by using kind of large virtual warehouses or high memory warehouses, along with a horizontal scale of distributed processing. What this entails is it reduces network traffic across our notebook environment to our database and leverages the extensive RBAC controls that we already have in place in Snowflake. We're also kind of looking at attribute-based access control as well. So we have our security tightly managed. So with this launch of Snowpark ML, we've started to design kind of data processing patterns. Now, this can also be for the data wrangling piece as well, but just let's focus here on feature engineering. So we've 3 patterns and not one solution fits all use cases. So in Fidelity, we do allow data scientists to access the data from our enterprise data lake. They're shown on the left from our raw data, using one of the Snowflake or Snowpark connector APIs and loading that data into a Pandas data frame. Now, this pattern also can apply to Spark ML. A lot of the data scientists leverage common feature engineering functions within scikit-learn. They do all their processing within the Pandas data frame and then load their feature set back into either our offline feature store in Snowflake or in the data scientist's custom data schema. So that's pattern A. What are the kind of core advantages and disadvantages of this pattern? First of all, we're able to access all Python libraries and all Python versions. And this is important when we talk about some of the restrictions currently in Snowpark. Data scientists are obviously very familiar with Python, and the Pandas data frame object is a very flexible data structure. Not only does it have columnar metadata, but it also has row metadata. So you might think of row indexing, for example, is a very important attribute to have in data science. Compatibility with other Python libraries is extensive, especially for data visualization. So that's one thing we find is lacking within the Snowflake environment, whereby our data scientists will want to kind of visualize the data, leveraging kind of the common visualization tools such as Matplotlib and Seaborn, etc. So some of the disadvantages of this pattern. is our data is transferred across the network. If it's large volumes, we have to spin up very large notebook environments so that the data fits in memory. Bear in mind, the data in Snowflake is compressed. When we feed it into a Pandas data frame, it becomes uncompressed. And we also need to allow for 5 to 10 times the memory size for a data set. We're typically restricted by a single node processing in Pandas, and we have to manage security. Our RBAC methods and framework have to come across into our notebook environment. So this pattern is generally for smaller volumes of data that's in use at the moment. So our second pattern is in database processing using SQL functions. This is in use in Fidelity for some data scientists, where we access the data from Snowflake, we connect using one of the APIs, and then we would call SQL functions and commands on a kind of a cursor-like object. That data is processed in database, and the data scientist will then generate their feature set and load it into Snowflake. Snowflake is our offline feature store. That's the approach we've taken from an enterprise direction. So the movement of data is limited. So you might be looking at this going, okay, well, you're using SQL operations here. And I'll talk about one of the disadvantages there, because not all data scientists would be experts in SQL. But let's have a look at some of the common advantages. So our data is not duplicated nor transferred across the network. We're able to leverage push down optimization in the database. Scaling is both at vertical and horizontal because we've distributed data operations happening within Snowflake. Our data is securely managed. And another advantage here is there's tight integration with data engineering or ML engineering, whereby generally what happens is the data scientists typically write in Python, hand over their scripts to our ML engineering team for productionization. So there's a kind of a translation has to happen. With pure SQL, that does not need to occur. So that sounds good as a pattern. However, most data scientists are not familiar with advanced SQL. There is a lack of complex data structures in Snowflake. So we don't have row indexing, for example. They're not as flexible, the structures in Snowflake, as there are in Pandas. There is a lack of built-in data science functionality, and we have the lack of data visualization within Snowflake. So now the third pattern is in database processing using Snowpark ML. So just to remind you, this is an additional library that exposes some of the common feature engineering techniques that you would find in Spark ML and scikit-learn. They're native to Snowflake. So both the storage and the compute are within Snowflake. We leverage the Snowpark connector, the Snowpark API, with the additional library installed. And we are exposed to some of the common feature engineering functions within this library. All the computation for feature engineering is pushed down into Snowflake. And then when the data scientist is happy with the resulting feature set, they would load that data either into their personal schema or ultimately hand over their scripts for operationalization into our model ops lifecycle. So very similar to SQL, our data is not duplicated nor transferred across the network. We're able to do large volume processing within the database. The whole concept of Snowpark data frames and Snowpark ML is it leverages lazy evaluation, which avoids unnecessary computation. Now, there is a slight downside to lazy evaluation. It both scales vertically and horizontally. Data is securely managed. Now, these functions are very similar to scikit-learn, but they're written slightly, there's a slight variation, but they're highly compatible with scikit-learn and Spark ML functions. So what are the downsides to this currently? Now, this was released public preview yesterday, Snowpark ML. And while we were developing this in private preview, we were restricted to use Python 3.8, even though our default notebook environment had gone up to 3.10. So we had to create a custom Conda environment with a lower version and test this functionality out. Now, in the keynote speak yesterday, there is support now for Python 3.9 and 3.10. But we do want to ensure that Snowflake are kept on top of these Python versions. I think in PyCon in April of this year in Utah, there was an announcement of Python 3.12, which we're looking forward to using because it really starts to look at optimizing memory within the Python packages. So Snowflake needs to be in step with Python versions. There is limited functionality currently. So Ray's going to talk about some of the common functions that are available, but we are working closely with Snowflake's team to ensure that we get a comprehensive suite of these techniques in the package. Another thing, debugging can be a challenge because of lazy evaluation. So it's only when you do a show or collect method that your code will execute. And if there's an issue within that pipeline, it can sometimes be hard to debug. So I've kind of talked about our data science journey. The issue we're now looking at due to large volumes is compute. And I think at one of the keynotes, it was, bringing compute to the data, not the other way around. And that's kind of one of our key guiding principles. So I'm going to hand it over now to Ray, and he's going to walk through how we would implement some of these techniques.
Thank you, Linda. So I'm going to talk about the feature engineering using the Snowpark ML. I think as the name suggests, Snowpark ML extension of the Snowpark, right? The Snowpark at the core is a Snowpark data frames. The data in the Snowpark data frame is being lazily evaluated. There are two sets of APIs. The first one is a transformation, right? Those APIs calls like select, filter. There's not actually results in execution. They just build a compute graph. The other set of APIs is actions like a show, collect, send to the table. They're triggered at execution. There are several benefits of using lazy evaluation. The first one is execution efficiency, right? So because with this compute graph, with optimizer, you can find out what computation is not needed in the final result. So you can just eliminate. And also it can combine multiple operations and done in the same path instead of multiple paths. The other benefit is memory efficiency. When you build a complex pipeline, the compute graph, right? If you evaluate it eagerly, you could end up with a lot of temporary tables. With memory efficiency, all the temporary results just automatically get discarded unless the user you explicitly would like to save into an external table. So today we are going to show like three features, right? Min-max scalar, one-hot encoding, and the Pearson correlation and Pearson correlation matrix, right? We'll show them in the order of the model development lifecycle. So the first thing I'm going to talk about is min-max scaling. So what does min-max scaling do is before you turn your data into model-ready data, this is a very important step. For numerical values, you want to scale the data into a fixed range, in this case between 0 and 1. This is the code how we're doing using pandas, right? As you can see, we create a min-max scalar. That's the fit. What the fit call is actually just calculate the maximum value and minimum value of those features. Well, the transform is just use the sample's current value minus the minimum value, and use the results to divide the difference between min and max. And finally, we save the data back into the Snowflake table. As you can see, this code is perfect fine if you're using Titanic data sets, which is very small. But this code is not going to scale if we use millions of rows, thousands of columns. we have to implement a function, right? What it does is we export the data in the data frames into a CSV files and move them into a Snowflake storage integration folders, and then using the copy command, copy into a Snowflake table. This can result like a 3x performance improvement. But still, this is very slow. So before this Snowpark ML, we can implement the min-max scaling 100% in SQL. Here's an example. You can see inside this select is just to calculate the min and max value, right? Also select is thus the scaling. By doing so is just we are doing the computation within the database instead of reloading the memory. And this effectively just remove this data move. And finally, this is with the Snowpark ML. You can see how this code is being done. We just have to import this Snow ML from the pre-processing package, create a min-max scaler called the fit, doing the transform. These are just building computer graph. And finally, the save the table is just going to, is actually execute the graph. Here's a performance comparison. As you can see, when we're using Snowpark ML or using natural SQL, because we eliminated data movement costs, it's much more efficient, right? You see, majority of time with Panda, scikit-learn has been spent moving data out and then putting the back and saving the data back in. And this task was done with with 28 million rows, 25 columns, and 5 gig in data set size. So I think actually this morning, I'm not sure if people has attended this builder keynote speech, right? And in there, they also give an example using standard scaling, right? The standard scaling, what it does is they first load the data into the Snowpark data frame and do a 2 pandas, and then call the min-max scaling. But because they load into pandas, right, and then doing the scaling, it takes like 30 seconds versus just 1 second if you just using this as a standard scaling with Snowpark ML provides. The next thing I'm going to talk about is one-hot encoding. Right? One-hot encoding is another important feature transformation technique when you're dealing with categorical values. Typically, like if you have a categorical variables has n-distinct values, the output of this one-hot encoding is a sparse matrix, right, with 7 columns. With any different columns, each column just has either 0 and 1s. This is how doing the one-hot encoding within this using the scikit-learn. As you can see, you have the loaded data into the independent data frames, and also doing feature transform. The output of this have like 7 different columns, things like each column like a Mr., Mrs., but only one of the column value can have each sample, right? Only one of the column value can have value of 1. And then at the end, we write the data back into the Snowflake table. This is how the code done within the Snowpark ML. The usage is very similar, right? It seems very similar APIs can fit, transform, and write it back to the table. But the performance is very different. As you can see, in Snowpark ML, we eliminated a data read and data write. And, this cut the most of the execution time. And also, by using this distributed parallelism, you can see this is doing data transformation is also fast. So previously, we talked about min-max scaler and also one-hot encoding. Most of the performance improvements is because we eliminated data movement costs. So for Pearson correlation and the Pearson correlation matrix calculation, we are going to show by scaling the computation both vertically and horizontally, it can result significant performance improvement. So Pearson correlation is just is very common techniques when you're doing this, trying to study if 2 feature variables, if there's a collinearity between 2 features, right? And also, sometimes we're perform the feature selections. You wanted to get rid of features that are highly correlated. In scikit-learn and append the data frame, there's an API called a core. What it does is just given like n columns, right? A data set with n column, the output is n by n matrix, which each cell is represent the correlation between those two, the correlation value of these two features. Unfortunately, this correlation dependence implementation is very inefficient, right? You can see this, the time complexity to be m times n squared, where m represent number of the rows and n represent the number of the columns. So for small data sets, we're able to get around with. For larger data sets, we have some use cases which has 29 million rows and over 4,000 columns. Even we find the largest single nodes, we still run into out of memory. So how do we address this solve problem? We have an in-house solution to one point in time. We're trying to, because there are m columns, which there's m choose 2 pairs of features. So we're trying to divide those feature pairs into buckets, and with each bucket, we'll create a SQL statement, and we send those SQL statements with along with like invoking this Snowflake core functions and compute these correlations, and we manually fill in this matrix ourselves. Doing so, we are able to achieve like a 3x to 5x performance improvement, but unfortunately, this still takes too long. So typically, our data scientists, before he leave for the night, he submitted the job, and the next day, he came back and checked the results. But that was the time we approached like Snowflake engineering team. Say, could you really help us? Because this just take too long. The kudos to like Garrett, Pradeep, and all of the Snowflake folks. They came with back as much like a parallelized version implementation. As you can see, this is how you're using the correlation call. You create the data assuming it's in the Snowpark data frames, and the correlation is by using the data when you scale both horizontally and vertically, it's can result in the magnitude of performance improvement. Here you can see there's some performance number. You can see with this is a Snowpark, the computation is a magnitude faster than the dependence implementation. So we have talk about like a min-max scaling, min-max scaler, one-hot encoder, and like the correlation analysis. I want to emphasize is in like feature engineering, feature selection, along with explore data analysis, take about 80% of the like this model development life cycle. So that's why we think it's very important. We need to speed up those kind of computation, and by speed it up, it can allow us the data scientists to iterate faster, and with the saved time, we can try out additional features, explore different new algorithms, and they improve the model performance. With that, I'm giving the control back to Linda.
Thanks, Ray. So in conclusion, what we're finding with Snowpark ML is it brings the compute closer to the data. I do want to call out a few little issues we've had along the way. The testing of this functionality, don't underestimate it. It takes a lot of time because we want to trial it on different volume sets, different warehouse sizes, different, Jupyter or notebook environment sizes. So that can take time. Now we're lucky in Fidelity, we have this concept of an internal internship within one of our business units where if associates want to skill up, they can kind of contribute to some of the work we're doing. So that's really, from a learning and development perspective, very efficient. As I said earlier, not all functionality is within Snowpark ML yet. And now that we're here in the summit, and we've been exposed to some new capabilities coming down the line on their roadmap, myself and Ray and the team will be looking at evaluating additional capabilities, in particular the containerization or the container services. So we're especially looking forward to evaluating that. Another thing that we'll be looking at in Fidelity is the iceberg table format to see can that increase our kind of flexibility within our model development process. Python version restrictions, and you might find this if you're using Snowpark for Python API currently, that the kind of package management needs to be addressed by Snowflake, along with being in lockstep with the later versions of Python itself. And finally, this is all great, and myself and Ray have done the evaluation, but we really need to start to educate our data scientists with some of this more new tooling available to try and accelerate their model development processing. And last but not least, we would like to thank Snowflake for the collaboration efforts. In particular, I've mentioned Ed, Garrett, and Pradeep, who have worked very closely and tirelessly with the team. So with that, thank you everyone for listening.